Hi, I'm Chris Pidden. Welcome to the fourth YOU SYNTH development blog. Last time I was investigating the problems with the electronics that detected and rectified a hit on the contact drum pads. After much experimentation with the electronics, I decided to abandon using electronics to do the detection and put the audio frequency analog straight into the microcontroller and do all the detection in software. I decided to look at it on the PC just using sound files because it's a lot easier to work on software in a PC than in a hardware environment like the Explorer board. So what I did, I recorded this, which is just the standard plywood pad. So we got this, and I also took a metal bracket, which you'll see in the picture, and recorded that, tapped with my finger. And took a recording of tapping it with a pair of scissors, in fact, which sounds like this. Okay, so then I wrote a program in Rad Studio to process those files. So this is the interesting function, the process sample function. So what I decided to do was run my audio at 16 kilohertz, because on looking at the Explorer board code, it was already sampling at 14 kilohertz. So what this program is doing is taking the audio sampled at 44 kilohertz and downsampling it to 16 kilohertz, and also dropping the bit rate to 10 bits, which is the number of bits in the A to D in the PIC. So this is the important function. It's called every 16 kilohertz sample. First thing I do is scale the sample up to a 15-bit number. This little bit of code is doing two things. It's calculating the difference between the midpoint, because the sample is not biased around zero, it's biased to an arbitrary point at about half the maximum sample. So this bit of code does two things. It rectifies the sample into this diff variable and updates the midpoint. The next thing it does is form an envelope. We want the envelope to rise sharply. So if the diff is greater than the envelope, it just follows it, and otherwise it decays to relatively slow exponential. Now here we have a little boolean variable which just says whether the envelope is on or off, and if it's off, we're maintaining the minimum value, and we're looking to see if it's turned on, so the envelope is greater than some absolute floor, and the envelope is actually twice the minimum. And if that's the case, we set the envelope on to true, we start tracking the maximum value, and we start this count variable which just counts for 2 milliseconds, and we assume we've had the maximum value in 2 milliseconds. Okay, so here is where the envelope on is true, the envelope is running, so we keep track of the maximum value and normally just count the counter. If the counter has timed out 2 milliseconds, well, all this one does is print the sample point and the maximum value on the screen, and then it sets the envelope onto false and starts tracking the minimum value again. Down here at the bottom we're just outputting the nmax and nmin values to a file so I can look at them. Okay, so let's run this program. Here we go. Ignoring most of this, it's just development stuff. We'll actually run it on the finger tap of the bracket, because that produces the most interesting results, and we hit run, and there we go. So this is the interesting bit. This gives the sample at which the event occurred and this is just an arbitrary value, but you can see we're getting 600 to 1600, which is a good dynamic range. So at this point I'm happy with the functioning of the program, so I'm going to try and port the code down into the Explorer board and try running it properly. Okay, so here we have the same code essentially in the PIC code in MPLabX in a function called process samples. This is called from the A to D interrupt, which I'll show you in a minute. As you can see, it's the same. The only difference is that we're doing it for, in fact, 8 channels here, and a lot of the bits of data for each channel has been gathered into a structure to make the code neater. Apart from that, it's essentially the same as what we had in the PC code. Now, if we go here, we have the A to D interrupt, which just loads all the values into a buffer and calls the process samples function I just showed you. Another interesting thing here is it sets the port line high at the start and low at the end. Okay, let's fire this up. And off she goes. Now my main worry about this will be the amount of processing time that this function would take, which is why we've got this port line in here. So if I now fire up the oscilloscope, so it is taking up most of the processor time, but it is leaving enough to do everything else. And if we measure the frequency, we can see it's running at 16.67 kilohertz, which is a good rate. And if we measure the high pulse width, we can see it's taking 40 microseconds, and if I actually play the drum it takes a bit more, but not a lot. So shall we see how it performs? Okay, so it's all programmed in. The question is, does it work? So the answer is yes, and we get a reasonable amount of dynamic range. Unfortunately, it's not particularly reliable, so I've got some serious debugging to do. Now, to debug something like this that's working in real time, I need to be able to get data out at a high rate, for which I will need RS485. I'll be telling you more about RS485 and how it relates to YOU SYNTH in the next video blog. For now, goodbye.